Hello, my name is Isaac Johnson, and today I'd like to discuss with you about predictive models and the stability of our solar system. So predicting the solar system is an age-old problem for cultural, religious, and scientific reasons. For example, the Maya culture had accurate tables of Venus and the moon around the 11th and 12th centuries. Categories of prediction include observation, calculation, and dynamical theory. And exemplars respectively are Tycho Brahe, Johannes Kepler, and Isaac Newton. Tycho Brahe had a device accurate to 32 arcseconds, roughly 1/120th of a degree, by the year 1586, which is astounding because the telescope wasn't invented until 1609. Today we will discuss some of the methods and history of prediction as well as the stability of the solar system. So, the first heliocentric laws came from Kepler. Kepler's first law claims that planets sweep out ellipses in their orbits, with the sun at the foci of the ellipse. Kepler's second law relates the sectors to the time it takes to go through an arc. So these are arcs, and the blue shaded regions are sectors. And so if you have two sectors that have the same area, that means that the planets sweep out those arcs in the same amount of time. Attempts to understand the solar system inspired great mathematical advancements. One example is the discovery of calculus by Newton and Leibniz. In 1687, Isaac Newton published his Principia Mathematica, which in this document was his universal law of gravitation, up here in the upper right. This provided a relation for gravitational forces. So the force is proportional to the product of the two bodies' masses and divided by the distance between them squared. Along with Newton's second law, F equals ma, we can calculate the acceleration produced, which is called the gravitational field strength. So this is the acceleration caused on object 1 by object 2. All we need now to start using this equation is the gravitational constant g. In 1798, Henry Cavendish experimentally discovered the proportionality constant. This was done by using well-balanced masses on a wire. So at the time, a relation was known between the torsional force in the wire and the angle that the wire had turned from equilibrium. This, along with knowledge of the masses and the distance between the two masses, allowed g to be calculated experimentally. And with a knowledge of Earth's radius, thanks to Eratosthenes, its mass could now be ascertained, which is why this experiment by Cavendish is known as weighing the world. This was crucial in calculating the masses of other solar system objects. Because if you know the distance from, say, the Earth to the sun, and you now know the Earth's mass, you can now calculate the sun's mass. And as far as finding the distance to the sun, that requires geometers. Vector analysis was invented and used in the 19th century. It was inspired by electricity and magnetism, and it allows us to notate the same ideas with less space and more clarity. Each vector represents three equations for our purposes due to the three-dimensionality of our space. So you can see these are Newton's universal laws of gravitation up here. They're just written with these vectors which point in the right direction. So R1 minus R2 points from R2 to R1. And then we have to divide by the magnitude cubed because we've essentially put an extra term in the numerator. So we have to divide it out in the denominator. As you can see from the reference of an origin, we have R1 is the vector that points from the origin to M1, R2 points from the origin to M2, and then the forces caused by gravity point from one mass to the other, and the forces are collinear to the distance between the objects. Acceleration, thanks to calculus, was discovered as the second time derivative of position. This allowed us to write Newton's laws as differential equations. And these differential equations describe how a system will behave next, given its current state. So as you can see, here's the gravitational field strength equation that tells you what the acceleration on the object is given the distance from the other object. The issue here is that acceleration will make something change its position. And so new position means new acceleration. So as R changes, A changes, and as A changes, R changes. And so with this relationship, we kind of have to calculate that feedback loop. And that's what this differential equation is going to do. And at the bottom here, the differential equation is written in vector form. Differential equations have a tendency of being much harder to solve than they are to write. So for the general two-body problem, each body will be affecting the other's motion. So this system will be governed by a system of two vector differential equations, as seen here to the right. And each vector equation represents three equations. So this would be the acceleration caused on object 1 by object 2, and this would be the acceleration on object 2 caused by object 1. And the distance between them would be what's here in the denominator. So differential equations describe how any such system would evolve in time. And for this reason, how the system began is vital to finding a particular solution. And the general two-body system requires the initial positions of each object and their initial velocities. And we require three values for each required initial condition due to three dimensions in space. So everything we have discussed is designed for point objects with mass. However, planets are not point objects. But the diameter of a planet is made negligible by the distance it is from the other planet or sun. And for this reason, it can be reasonable as an approximation to treat our planets as point masses that reside within the planet's center. For planets with sizable moons, it is often best to treat the system of mass at the barycenter. The barycenter is the center of mass for the planet-moon system. So even though the general two-body problem works, we want to find a way to simplify it specifically. And so one way to do this is with the fixed central body approximation, which assumes that one body is much more massive than the other. So here I have mass 1 is much, much greater than mass 2. We then assume that the massive central body is the origin of the coordinate system. So you can see M1 here is at the center. We're going to assume it's not going to move because it is so massive compared to the other planet. And because of this, the differential equation for the acceleration of the massive object just equals 0. So it won't move. And what we're left with is just a single differential equation of which to solve to find R2 solution. So here are some solutions to the fixed central body approximation. As Kepler's laws predicted, bound orbital solutions are ellipses. See, this blue path right here would be an example of an elliptical orbit. Whereas unbound solutions exist and include parabolic and hyperbolic orbits. Right here, we have an unbound orbit because this red, the object that's going along the red curve will end up being ejected from the gravitational influence of the sun, and it won't come back to loop around. For our purposes, we are really only interested in bound orbits. And most of the planets in our solar system have very low eccentricity. And what that means is that most of the planet orbits in our solar system are nearly circular. So for our solar system, if you take all the 8 planets' masses combined, that only accounts for about 0.135% of the sun's mass. That means that forces between the planets are minuscule in comparison to the sun's influence. I have a table over here which shows the gravitational field strength at nearest approach between several objects. The first chart shows the acceleration on Earth caused by, say, the Sun, Venus, Mars, Jupiter, and the Moon. We can see that the acceleration the Sun causes on the Earth at their nearest approach, also known as perihelion, is about 6.1 times 10 to the minus 3 meters per second squared. And the Moon's effect on Earth, the acceleration it causes on the Earth, is about 200 times less than the Sun's effect on the Earth. And on top of that, Jupiter's acceleration that it causes on the Earth is about 100 times less than the moon's acceleration it causes on the Earth. So then the second table is the same thing for Uranus with several different planets. And we can see here that the sun's effect on Uranus is 1 times 10 to the 4 times greater than any other object, or times 10 to the 3. So the sun definitely has the primary effect on these planets. And so for these reasons, a good first approximation for our solar system is to ignore the effects between the planets. This leads us to perturbation theory. Now that we have a good first approximation, we can start using perturbative methods. A perturbative method starts with a known solution to a simplified problem, which is called the 0th order approximation. Over here, it's notated as A0. Then successive terms are added to these known solutions, such as epsilon A1 plus epsilon squared A2, and so on. And so these extra terms increase the adherence to the true orbit solution. So as you can see over here, we have body 1, which is the sun for our case. We have this body that has this orbit called the oscillating orbit. That's the orbit of the fixed central body approximation. So imagine that's the Earth. And then say body 2 is Jupiter. So this is the orbit the Earth would take, but because of the second body, there's a slightly different acceleration, which changes the orbit into what's called the true orbit or the perturbed orbit. So the new problem now is going to include planetary gravitational effects. So now the differential equation looks a lot bigger. This would be the acceleration on the ith object, and the acceleration would be comprised of the acceleration on that object caused by the sun, which is definitely the most massive term. And then this summation over here includes the accelerations caused by the other planets in the system on the ith planet. And I does not equal J because a planet cannot exert a gravitational force on itself from the system scale. In the same way, I can't pull myself up by my own bootstraps. So the goal of perturbative methods is to just get an accurate approximation, as accurate as you would like to have it. And we do this by starting with the fixed central body approximation, which is the 0th order approximation. Then we add less significant terms. And this increases the adherence of the solution to the new differential equations. And it's important to say that even though it's called perturbation theory, it is comprised of many perturbative methods, and not all of them are really related in any sense, except that they all start with a 0th order approximation, and then there's methods to adding on less significant terms. So that leads us to one of the great crowning accomplishments of perturbation theory and Newtonian mechanics, the discovery of Neptune. So Uranus was discovered in 1781 by Caroline and William Herschel. And observations were done for the next 66 years, which is roughly 1 Uranian year. And data did not match the predictions. It was off by about 21 arc seconds, which was well within the measurement of the time. Like, it was definitely doable for the time, especially considering hundreds of years before Tycho Brahe was measuring things with that kind of accuracy. So in 1846, John Coche Adams and Leverrier independently predicted a planet further away from the sun than Uranus. It turns out they sent their predictions to astronomers, told them where to look and when to look in the sky. And lo and behold, a new planet was discovered, Neptune. And to me, that story is just incredible. This is before really modern computing or computing at all. I mean, computation was all by hand. And these perturbative methods require iterative processes that can be very time consuming. So it's really an impressive discovery. And yeah, Neptune was the first planet discovered mathematically. So over here we have a plot of not Uranus's orbit. This is a simulation of an Earth-like orbit. So you can see The y-axis is the distance the Earth is away from the sun, and the x-axis is time in years, Earth years. So with the blue oscillation, that's the unperturbed orbit of Earth. In other words, with the fixed central body approximation, this is what the plot looks like. But then I added a massive solar system body that was just outside of Earth. And I kind of exaggerated it a little bit so that the graph looked a little more pleasing and easy to decipher. And so the yellow plot, the yellow curve, shows the perturbed orbit, and the perturbations were caused by that larger outer mass. And so in a similar way, this is kind of how Uranus was discovered. It's just they only had one Uranian year, so they really only had one of these humps to look at the data for. So let's talk about the stability of our solar system. During Newton's time, stability was more of a theological question. I mean, a lot of them believed the solar system would end because of theological reasons, supernatural intervention. But nobody really necessarily thought that it would be a scientific mechanism that brought about the destruction of the solar system. And later in the Enlightenment period, this brought thinkers that viewed stability as a scientific question. One of them was Laplace. And in 1773, Laplace proved that the solar system orbits are periodic. But because of perturbative effects, those periods are very, very long. But he did prove at the time that the solar system orbits are periodic, which in a sense kind of secured this idea of stability and Laplacian determinism. But in 1887, Henry Poincaré proved that no closed form general solution exists for a system of three or more bodies. And this question is still explored today, especially with the advent of modern computing. So it turns out stability is all about the time scale. Our solar system is independently very stable. However, over extremely large timescales, the solar system falls into the category of chaos theory. Chaos theory describes systems that diverge greatly with small changes to initial conditions. An example is the double pendulum, which there's an animation to the right. You see that for a while there, from the beginning, it looks like they started with the same initial condition, and it looks like they're following the same paths. But then over time, you start noticing small differences and then great differences. They start diverging. That's a good example of chaos theory. So because of Poincaré's proof, it is likely that determinism for our solar system is off the table for now. So let's talk about numerical simulations. I looked at a paper where it was published, numerical simulations using classical mechanics, which is essentially what we just talked about today. That means that it neglected relativistic effects and extra solar system effects as well. These simulations showed very little serious instability from on a timescale of about 20 billion years. That's a long time. As a matter of fact, it's most likely that the sun will envelop Earth's orbit as it swells into a giant star by about 7.5 billion years. So truly, this numerical simulation doesn't really account for, all the other things that could happen. It's just looking at kind of the uniformity. And some of the results showed Mercury falling into the sun at a certain time, or Mercury colliding with Venus. And you can see that Earth's eccentricity is quite stable. So whereas Mercury's varies wildly, which might explain its instability. So what we learned and talked about today is modern dynamical theories of our solar system, and they are around 4 centuries old. The problem has a rich and deep history, and mathematics has advanced and will continue to advance greatly due to this problem. With new methods and computing, it seems our solar system is very stable over long periods of time, which is good news. All right, thank you for being here. Bye.